Good morning, everyone. Hopefully it's morning where you are. It's morning here in Pearland, Texas. Beautiful day here. A little bit cool, probably in the 60s, but yesterday was in almost 80 here. So beautiful day. But anyway, I want to start off today talking about the fact that we're going to discuss the road to continuous improvement, specifically process safety information. I've broken this down into two different parts. In the first part, we're going to be talking about the technology, the process, and then the second part, we're going to be talking about the technology, the process safety information as it pertains to toxicity, et cetera. So we're going to break this down into two different parts. Like I said, the next session we'll do on a webinar, we'll cover the second part of process safety information, which is the technology of the equipment. So process safety information is information pertaining to the hazards of the highly hazardous material. That's part of it. In other words, it's an HHC, or highly hazardous chemical. Information pertaining to the technology of the process, and that's basis for equipment design. So like I said, within process safety information, you can break this down into three distinct areas. Mainly, like I said, information pertaining to the hazard of the chemical itself, or the hazardous material. It's information pertaining to the technology of the process, and information pertaining to the equipment in the process. So if you look at this in real terms, as we design processes, typically we start out looking at what materials will the process and what handle, what materials will be processed in the facility, et cetera. So we need to make sure that we understand those hazards of those chemicals as we begin to design the equipment. Once we understand those hazards, then we can start designing, and that is the design basis for most of the equipment that we'll talk about during our next session. The other piece of that is the technology of the process itself. Is how does the process work? How is it going to work? What is the description of the various process events that will take place as you produce that final product? It's important to understand those three distinct portions of the PSI. If you don't begin to understand those, and it's hard to really see where all of the process safety information kind of works together. If we keep in mind that the first parts and first elements of PSM really have to do with design, then we'll begin to see that how all of these elements of PSM actually fit together to provide process safety. The last portion of process safety information, if you look at the PSM standard itself, it talks about you must document that equipment complies with REGA-GAP. That's usually something distinct and different than the first three parts of the process safety information requirement. Once you do all of the equipment design, then of course all you need to do then is document that it complies with your recognized and generally accepted good engineering practices. This must all be done before conducting a PHA. That's the important part. Many of you, if you've ever been into one of my PSM training courses and classes, you'll know that we spend a lot of time on process safety information because it's so important. For those of you that remember the day where there used to be a saying, trash in, trash out, as it related to computer input. The same way here. Essentially, if your process safety information is inaccurate, incomplete, so your PHA, your process hazards analysis, you won't be able to manage the risk in your process if you don't know the information that's contained in it. So let's look at the regulation real quick, and I'm not going to read this whole thing, but essentially it talks about in accordance with the schedule set forth in paragraph E1. E1 is being the PHA element of PSM. The employer shall complete a compilation of written process safety information before conducting any process hazards analysis required by the standard. So it really says that you need to compile all that information before doing the PHA. As I stated earlier, You know, you don't have accurate process safety information, then your PHA is not going to be very accurate as well. So let's talk about the different parts. We're going to talk about the first part, D1I first, and that's information pertaining to the hazards of the highly hazardous chemicals in the process. Its information shall consist of at least the following: toxicity information, permissible exposure limits, physical data, reactivity data, corrosivity data, thermal and chemical stability data, hazardous effects of intermittent mixing, inadvertent mixing of different materials that could foreseeably occur. Most people will fulfill this portion of the requirement through a safety data sheets, and most of your safety data sheets will contain this information. Some of the information that will not contain in a lot of cases is the inadvertent mixing of the different materials. There's no way they could foreseeably see every possible scenario of mixing that chemical with something else. So you as a facility must look at that specifically to determine if there's any hazardous effects of inadvertent mixing with the chemicals that you actually have in your process. So the purpose and the intent of the process safety information, like we said earlier, is to compile accurate and process safety information, or PSI. It has to do with chemicals, it has to do with chemistry, it has to do with all of your equipment, it has to do with all your safety systems. Many times I say if it's on a P&ID, then you must have process safety information regarding that equipment, the chemistry, how is it built, what the materials construction, et cetera, et cetera. The other thing is you must have safe upper and lower limits and the consequence of deviation from those limits. This particular item here is probably gets more confusion than anything within the PSM community. A lot of times I will see during audits that safe upper and lower limits are actually incorporated in operating procedures. Let's not confuse the two. When we talk about safe upper and lower limits, we're talking about process safety information. The key word in that is process. So what are the process safety limits? Limits to the process itself, not limits to the equipment, not limits to operating limits, none of those things. It should be the basis, and this information should be the basis, like we said, for process hazards analysis. Typically, we can look at process safety information as design information. What are those things that information that we used first to design the equipment, and then what and how the equipment is actually designed. Again, like I said, you can use an SDS. Normally you'll have your basic chemical data, like your chemical name, identification, manufacturer, emergency contact information. If you're familiar with the SDS, you know that it has 16 different sections, and all of those sections have various information regarding that chemical. And that can fulfill, like I said, most of the information that you need for toxicity information regarding the chemicals in your process. Some additional information that you can find on the SDS is you know, the composition of the chemical itself. That can help you to determine whether or not you have any inadvertent mixing type issues as well. Any firefighting measures that you can put perhaps in your emergency response procedures, accidental release measures, also emergency response, maybe even information that can go in your SOPs. Handling and storage, obviously in your operating procedures, but also could be in actually design of equipment. And of course, any toxicology information and then ecological information as well. So there's a host of information that the SDS can provide as part of your requirement to find toxicity information. The next part of the process safety information is the information concerning the technology of the process, and it shall include at least the following: a block flow diagram or simplified process flow diagram, maybe a process chemistry, maximum intended inventory, and again, these safe upper and lower limits for such items as temperatures, pressures, flows, and composition. And then, of course, an evaluation of the consequences of deviation, including those affecting safety and health of employees. So we all probably are pretty familiar with what a block flow diagram is. They could be, they should be something that's very high level. So if I can take anybody that comes into my process and I can take about 5 to 10 minutes to give them a high level process overview, one of the things that I may pull out is the block flow diagram, kind of explain what we do and how we do it. Again, a very high level overview of the process. Should contain basic process overview, should be for something that we use for new operators when they're first coming on board. We don't want them, typically we will not throw a set of P&IDs in front of them and say, this is how the process works. It'd be very difficult to go through a process using P&IDs. It's much easier to start out with a simplified flow diagram to kind of show the overview of how the process works and the various components within the process itself. Again, great for new engineers, technicians as well, even managers that come on site. They may not need to know all of the details on how the process works, but certainly an overview would be appropriate. Process chemistry should include an overview of the process in writing. I've seen process descriptions that have been pages and pages of documentation written by PhDs that essentially designed the process. That is not particularly what they're looking for here, but a basic overview again of how the process works in writing. And so it should be something that operators, managers, technicians, and engineers can certainly pick up and read and understand in basic terms how that process works. Nothing wrong with having those details, but not necessarily in your process chemistry overview. Should include the major steps and phases, things like reactions, separations of liquids and gases, compression, dehydration, blending and mixing, storage, etc. And really how each step is accomplished, again, in very basic terms. So some of the common gaps that we see in these first two sets of process safety information is really depending on the process. As you know, PSM covers a multitude of different processes. We've got ammonia refrigeration, for example. You have anhydrous ammonia, so that's the chemical involved there. Completely different process than what you'd see at a midstream gas plant, for example. Certainly different than what you'd see in a refinery. Certainly different than you'd see in a chemical plant or a specialty chemicals facility or a blending facility for that matter. So all of the gaps somewhat will depend on process. Most of the time what we see is lack of toxicity information for intermediate products. And what we mean by that is, let's say that you work at a petrochemical facility or specialty chemical plant. You may take in raw materials that have an SDS that are associated with it, so you have a pretty good idea of the toxicity information for those chemicals. But as you go through your actual process, you begin to alter those incoming products and break intermediate products on your way to the finished product that you're trying to make. Sometimes those intermediate products have toxicity that's much, much worse than the final product or even their intermediate or raw materials that are coming in. So those intermediate products, if they're in the threshold quantities, must also have process safety information and toxicity information associated with those. So those need to be developed just like you would develop any raw material toxicity information and any finished product toxicity information as well. Inaccurate maximum intended inventory. See this quite often where the maximum intended inventory information is provided, but it doesn't really reflect what they currently have in their inventory. Sometimes the inventory is based on a number rather than actual what is their intended inventory throughout the process. So what I mean by that is maybe some will say, well, we only intend to have 30% in there. But then when you go into the control room and look at levels, they're running at 50. And it's easy to ask an operator, what do you normally run? And they'll say 50, 60%. Well, that needs to be reflected in your intended inventory because that's what you truly intend to maintain those levels. Maybe you don't maintain it that high all the time, but but certainly that's your maximum intended amount. Of course, the next gap we see is missing or inaccurate process chemistry. As we know, processes change all the time. We make improvements, we make changes to those processes, so that chemistry sometimes has to be updated as well. The bigger things is the lack of true safe upper and lower limits of the process. And then, of course, inaccurate safe and lower limits and consequences as well. So what are some of those next steps that you could take to make sure that you're addressing these two elements of process safety information? First, obviously, is develop the toxicity information for any intermediate chemicals that you might have. Sometimes that could be a task. The other part is actually looking at your toxicity information as it pertains to unintended mixing of other materials. So if you take a raw material and you're mixing with another raw material, et cetera, or you're doing a reaction, et cetera, those things must be looked at from a toxicity standpoint as well. Of course, develop and revise the process description to make it easily understood and document it. Oftentimes, some facilities, and this is true especially in ammonia refrigeration facilities, we see that they have not documented the process description. Even though it's a fairly simple process, you still must document it. Again, it's a way to communicate your process to others that come into your facility. It's a way to communicate your process to those first responders, for example, that may need to come in and respond to an incident in your facility. And all of this information that you can have available to those people, the quicker they can respond. And maybe rather than make it a recovery, they can make it a rescue instead. Must update the maximum intended inventory to reflect controls. So if you have controls in your process to control a level at 50%, then certainly that makes sense to be the maximum intended inventory because it's controlled there. On the other hand, if you have no controls and that level can vary from 10% to 80% with nothing to stop it, including SOPs, et cetera, then you need to set your maximum intended inventory accordingly. There is no benefit really from a regulatory standpoint not to set that as high as you need it to be. Certainly, citations can evolve if your maximum intended inventory is being exceeded, but there's no citations that can be issued if you don't exceed it. So rather than set at 50% and risk the chance of somebody coming into your facility and seeing at 60 or 70%, why not set it at 70 or 80% or at that control point to make sure that you never exceed that. Certainly, it should be part of your SOPs as well. Review and update safe upper and lower limits and document the consequences of deviation. Those are the next steps. So in order to do that, we must ask the question why. Why are vessels MAWPs what they are? For example, if you have a process and the majority of your equipment is running at 250, the MAWP of the vessel is 250 PSIG, we need to understand why it's 250. For example, if we look back at ammonia refrigeration, we know that if you look at all of the charts of vapor and pressure and temperature and everything else, you can see why the MAWP of vessels is at 250. Because the process itself may not be able to go above, say, 180 or 190, et cetera. So now if you add a safety factor to that maximum upper limit, safe limit, that's how you arrive at your MAWP of your vessels. Same goes with piping. Oftentimes, engineers will size piping to address a specific process safety issue. For example, not too long ago, we did an investigation on a fire that was a result of piping failure. The piping failure, as we began to do the investigation, we had noticed that the inlet piping at one point in time was 12-inch. And then shortly thereafter, not within about 2 or 3 years, it was replaced with 8-inch. And so as we begin to look further into the reasons why it was changed, we found that the engineer decided, to reduce some of the cost of an addition that they were making, could go with 8-inch pipe versus the 12-inch. Unbeknownst to him, however, the reason why it was 12-inch to begin with is because the inlet gas had a small amount of sand in it or silica, and that silica at a certain velocity, of course, would erode piping, and whenever it made changes in direction, elbows, etc., it would begin to erode that pipe away. So when they went to the 6-inch pipe, or the 8-inch pipe rather, the velocity increased significantly, and of course, so did erosion. It eroded the pipe and had a major release of gas and a fire and explosion that occurred. So this would be a safe limit. So this would be in terms of flows. So we want to limit the flow or the velocity in a pipe. That would be a safe limit that we'd want to make sure that we're documenting in our process safety information. Why can there not be more ammonia in the water or water in ammonia at very high levels? That's a composition issue. So if you look at IAR, for example, it limits how much water can be in your anhydrous ammonia. Why? Well, it increases corrosion, etc. So those are the consequences of the deviating from those safe limits. Same way with H2S, for example. Why are those levels maintained in your incoming gas streams, for example? We know that H2S, as it reaches much above 5 ppm to 10 ppm, can increase corrosion rates, etc. So we have the limit, we have a safe limit, say at 5 ppm. Consequence is, if we exceed that limit, is increased corrosion rates. If we think about all of these things that we just listed here, we can see that these are all things that go into the process of designing equipment. You know, the process engineer will sit down and say, okay, the plan is going to be designed for X amount of flow. That flow and composition is such, and that will be the basis in which we design all of the equipment from. So knowing and understanding and documenting these consequences and limits is very important in the initial design phase. Remember, if we're looking at these 3 elements from an initial design phase, these are the first things that we do in the process design. We need to understand why there are limits in pressure, why are there limits in temperatures and flows and compositions. And if we ask ourselves those questions, even up to and during the PHA, maybe we can document and find more of these issues that we need to address in our process safety information. So with that today, that I know is a short lesson on process safety information. We took the first 2 elements of that. Next time we're going to be talking about the process safety information as it pertains to the equipment in the process. It's going to take us a little bit longer, so I want to divide this up into smaller sections. So I will unmute everybody, and if you have any questions now, feel free to chime in. Or you can raise your hand or send me a chat question. I'll answer it that way as well. Okay, so everybody's kind of quiet today. Hopefully this didn't put you to sleep, but it was great having you all join us today. I want you to remember, like I said, next time we're going to be talking about process safety information as it pertains to equipment of the process. And that one's set for April 30th. And let's see, April 30th is right, April 30th. And feel free to join at any time. And again, I've got my email up here. You can email me with any questions, or you can call our office. We'll be able to answer anything that you have, okay? Thank you so much for joining, and we'll hopefully see you on April 30th. Have a great week. Bye.
Mm.